Welcome back, or welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled USB. Universal Serial Bus, USB, is an industry standard that allows data exchange and delivery of power between many types of connections. It specifies its architecture, in particular its physical interface, and communication protocols for data transfer and power delivery to and from hosts, such as personal computers, to and from peripheral devices, e.g., displays, keyboards, and mass storage devices, and to and from intermediate hubs, which multiply the number of a host's ports. Introduced in 1996, USB was originally designed to standardize the connection of peripherals to computers, replacing various interfaces such as serial ports, parallel ports, game ports, and ADP ports. Early versions of USB became commonplace on a wide range of devices, such as keyboards, mice, cameras, printers, scanners, flash drives, smartphones, game consoles, and power banks. USB has since evolved into a standard to replace virtually all common ports on computers, mobile devices, peripherals, power supplies, and manifold other small electronics. In the current standard, the USB-C connector replaces the many various connectors for power, up to 240 watts, displays, e.g., DisplayPort HDMI, and many other uses, as well as all previous USB connectors. As of 2024, USB consists of 4 generations of specifications: USB 1.x, USB 2.0, USB 3.x, and USB 4. USB 4 enhances the data transfer and power delivery functionality with a connection-oriented tunneling architecture designed to combine multiple protocols onto a single physical interface so that the total speed and performance of the USB 4 fabric can be dynamically shared. USB 4 particularly supports the tunneling of the Thunderbolt 3 protocol, namely PCI Express, PCIe Load Store Interface, and DisplayPort Display Interface. USB 4 also adds host-to-host interfaces. Each specification subversion supports different signaling rates from 1.5 and 12 megabit per second total in USB 1.0 to 80 gigabits per second in each direction in USB 4. USB also provides power to peripheral devices. The latest versions of the standard extend the power delivery limits for battery charging and devices requiring up to 240 watts. USB Power Delivery, USB PD. Over the years, USB PD has been adopted as the standard power supply and charging format for many mobile devices, such as mobile phones, reducing the need for proprietary chargers. USB was designed to standardize the connection of peripherals to personal computers, both to exchange data and to supply electric power. It has largely replaced interfaces such as serial ports and parallel ports, and has become commonplace on a wide range of devices. Examples of peripherals that are connected via USB include computer keyboards and mice, video cameras, printers, portable media players, mobile, portable, digital telephones, disk drives, and network adapters. USB connectors have been increasingly replacing other types of charging cables for portable devices. USB connector interfaces are classified into three types: the main various legacy Type A upstream and Type B downstream connectors found on hosts, hubs, and peripheral devices, and the modern Type C USB-C connector, which as of 2014 starts to replace all of the many legacy connectors and is the only applicable connector for USB 4. The Type A and Type B connectors came in standard, mini, and micro sizes. The standard format was the largest and was mainly used for desktop and larger peripheral equipment. The mini USB connectors, Mini A, Mini B, Mini AB, were introduced for mobile devices, but they were quickly replaced by thinner micro USB connectors, Micro A, Micro B, Micro AB. The Type C connector, also known as USB-C, is not exclusive to USB, is the only current standard for USB, is required for USB 4, and is required by other standards as well, including Modern DisplayPort and Thunderbolt. It is reversible and can support various functionalities and protocols, including USB. Some are mandatory, many optional, depending on the type of the hardware, host, peripheral device, or hub. USB specifications provide backward compatibility, but this usually results in a decrease in signaling rates, maximal power offered, and other provided capabilities. The USB 1.1 specification replaces USB 1.0. The USB 2.0 specification is backward compatible with USB 1.0 1.1. The USB 3.2 specification replaces USB 3.1 and USB 3.0, while also including the USB 2.0 specification. USB 4 functionally replaces USB 3.2, while retaining USB 2.0 bus operating in parallel. The USB 3.0 specification defined a new architecture and protocol named SuperSpeed, aka SuperSpeed USB, marketed as SS, which included a new lane for a new signal coding scheme, 8 bits per 10-bit symbols, 5 gigabits per second, later also known as Gen 1, providing full duplex data transfers that physically required 5 additional wires and pins, while preserving the USB 2.0 architecture and protocols, and therefore keeping the original 4 pins or wires for the USB 2.0 backward compatibility, resulting in 9 wires, with 9 or 10 pins at connector interfaces. ID pin is not wired in total. The USB 3.1 specification introduced an enhanced SuperSpeed system while preserving the SuperSpeed architecture and protocol, SuperSpeed USB, with an additional SuperSpeed Plus architecture and protocol, aka SuperSpeed Plus USB, adding a new coding schema, 128 bits per 132-bit symbols, 10 gigabits per second, also known as Gen 2, for some time period marketed as SuperSpeed Plus, SS Plus. The USB 3.2 specification added a second lane to the enhanced SuperSpeed system, besides other enhancements, so that the SuperSpeed Plus USB system part implements the Gen 1 by 2, Gen 2 by 1, and Gen 2 by 2 operation modes. The SuperSpeed USB part of the system, however, still implements the one-lane Gen 1 by 1 operation mode. Therefore, two-lane operations, namely USB 3.2, Gen 1 by 2, and Gen 2 by 2, are only possible with full-featured USB-C. As of 2023, they are somewhat rarely implemented. Intel, however, starts to include them in its 11th generation SoC processor models, but Apple never provided them. On the other hand, USB 3.2 Gen 1 and Gen 2 has been quite common for some years. Each USB connection is made using two connectors, a receptacle and a plug. The Universal Serial Bus was developed to simplify and improve the interface between personal computers and peripheral devices, such as cell phones, computer accessories, and monitors, when compared with previously existing standard or ad hoc proprietary interfaces. From the computer user's perspective, the USB interface improves ease of use in several ways. The USB interface is self-configuring, eliminating the need for the user to adjust the device's settings for speed or data format, or configure interrupts, input-output addresses, or direct memory access channels. USB connectors are standardized at the host, so any peripheral can use most available receptacles. USB takes full advantage of the additional processing power that can be economically put into peripheral devices so that they can manage themselves. As such, USB devices often do not have user-adjustable interface settings. The USB interface is hot swappable. Devices can be exchanged without shutting the host computer down. Small devices can be powered directly from the USB interface, eliminating the need for additional power supply cables. Because use of the USB logo is only permitted after compliance testing, the user can have confidence that a USB device will work as expected without extensive interaction with settings and configuration. The USB interface defines protocols for recovery from common errors, improving reliability over previous interfaces. Installing a device that relies on the USB standard requires minimal operator action. When a user plugs a device into a port on a running computer, it either entirely automatically configures using existing device drivers, or the system prompts a user to locate a driver, which it then installs and configures automatically. The USB standard also provides multiple benefits for hardware manufacturers and software developers, specifically in the relative ease of implementation. The USB standard eliminates the requirement to develop proprietary interfaces to new peripherals. The wide range of transfer speeds available for a USB interface suits devices ranging from keyboards and mice up to streaming video interfaces. A USB interface can be designed to provide the best available latency for time-critical functions, or can be set up to do background transfers of bulk data with little impact on system resources. The USB interface is generalized with no signal lines dedicated to only one function of one device. As with all standards, USB possesses multiple limitations to its design. USB cables are limited in length, as the standard was intended for peripherals on the same tabletop, not between rooms or buildings. However, a USB port can be connected to a gateway that accesses distant devices. USB data transfer rates are slower than those of other interconnects, such as 100 gigabit Ethernet. USB has a strict three-network topology and master-slave protocol for addressing peripheral devices. Those devices cannot interact with one another except via the host, and two hosts cannot communicate over their USB ports directly. Some extension to this limitation is possible through USB on the go, dual role devices, and protocol bridge. A host cannot broadcast signals to all peripherals at once. Each must be addressed individually. While converters exist between certain legacy interfaces in USB, they might not provide a full implementation of the legacy hardware. For example, a USB to parallel port converter might work well with a printer, but not with a scanner that requires bidirectional use of the data pins. For a product developer, using USB requires the implementation of a complex protocol and implies an intelligent controller in the peripheral device. Developers of USB devices intended for public sale generally must obtain a USB ID, which requires that they pay a fee to the USB Implementers Forum, USB-IF. Developers of products that use the USB specification must sign an agreement with the USB-IF. Use of the USB logo on the product requires annual fees and membership in the organization. A group of 7 companies began the development of USB in 1995. Compaq, DEC, IBM, Intel, Microsoft, NEC, and Nortel. The goal was to make it fundamentally easier to connect external devices to PCs by replacing the multitude of connectors at the back of PCs, addressing the usability issues of existing interfaces, and simplifying software configuration of all devices connected to USB, as well as permitting greater data transfer rates for external devices and plug-and-play features. Ajay Bhatt and his team worked on the standard at Intel. The first integrated circuits supporting USB were produced by Intel in 1995. Released in January 1996, USB 1.0 specified signaling rates of 1.5 megabits per second, low bandwidth or low speed, and 12 megabits per second, full speed. It did not allow for extension cables due to timing and power limitations. Few USB devices made it to the market until USB 1.1 was released in August 1998. USB 1.1 was the earliest revision that was widely adopted and led to what Microsoft designated the legacy-free PC. Neither USB 1.0 nor 1.1 specified a design for any connector smaller than the standard Type A or Type B. Though many designs for a miniaturized Type B connector appeared on many peripherals, conformity to the USB 1.x standard was hampered by treating peripherals that had miniature connectors as though they had a tethered connection, that is, no plug or receptacle at the peripheral end. There was no known miniature Type A connector until USB 2.0 introduced one. USB 2.0 was released in April 2000, adding a higher maximum signaling rate of 480 megabits per second, maximum theoretical data throughput 53 megabytes per second, named high speed or high bandwidth, in addition to the USB 1.x full speed signaling rate of 12 megabits per second, maximum theoretical data throughput 1.2 megabytes per second. Modifications to the USB specification have been made via engineering change notices, ECNs. The most important of these ECNs are included into the USB 2.0 specification package available from USB.org. Mini A and Mini B connector. Micro USB cables and connectors specification 1.01. Interchip USB supplement. On the Go supplement 1.3. USB on the go makes it possible for two USB devices to communicate with each other without requiring a separate USB host. Battery charging specification 1.1 added support for dedicated chargers, host chargers behavior for devices with dead batteries. Battery charging specification 1.2 with increased current of 1.5A on charging ports for unconfigured devices, allowing high-speed communication while having a current up to 1.5A. Link Power Management, Addendum ECN, which adds a sleep power state. The USB 3.0 specification was released on the 12th of November 2008, with its management transferring from USB 3.0 Promoter Group to the USB Implementers Forum, USBIF, and announced on the 17th of November 2008 at the Super Speed USB Developers Conference. USB 3.0 adds a new architecture and protocol named SuperSpeed, with associated backward compatible plugs, receptacles, and cables. SuperSpeed plugs and receptacles are identified with a distinct logo and blue inserts in standard format receptacles. The SuperSpeed architecture provides for an operation mode at a rate of 5 gigabits per second, in addition to the 3 existing operation modes. Its efficiency is dependent on a number of factors, including physical symbol encoding and link level overhead. At a 5 gigabits per second signaling rate with 8 bits per 10 bits encoding, each byte needs 10 bits to transmit. So the raw throughput is 500 megabits per second. When flow control, packet framing, and protocol overhead are considered, it is realistic for about 2/3 of the raw throughput, or 330 megabits per second, to transmit to an application. SuperSpeed's architecture is full duplex. All earlier implementations, USB 1.0 to 2.0, are all half duplex arbitrated by the host. Low power and high power devices remain operational with this standard, but devices implementing SuperSpeed can provide increased current of between 150 milliamps and 900 milliamps by discrete steps of 150 milliamps. USB 3.0 also introduced the USB attached CSCI protocol, UASP, which provides generally faster transfer speeds than the BOT, bulk-only transfer protocol. USB 3.1, released in July 2013, has two variants. The first one preserves USB 3.0's SuperSpeed architecture and protocol, and its operation mode is newly named USB 3.1 Gen 1. And the second version introduces a distinctively new SuperSpeed Plus architecture and protocol, with a second operation mode named as USB 3.1 Gen 2, marketed as SuperSpeed Plus USB. SuperSpeed Plus doubles the maximum signaling rate to 10 gigabits per second, later marketed as SuperSpeed USB 10 gigabits per second by the USB 3.2 specification. or reducing line encoding overhead to just 3% by changing the encoding scheme to 128 bits per 132 bits. USB 3.2, released in September 2017, preserves existing USB 3.1 SuperSpeed and SuperSpeed Plus architectures and protocols and their respective operation modes, but introduces two additional SuperSpeed Plus operation modes, USB 3.2 Gen 1 by 2 and USB 3.2 Gen 2 by 2, with the new USB-C fabric with signaling rates of 10 and 20 gigabits per second, raw data rates of 1212 and 2424 megabits per second. The increase in bandwidth is a result of two-lane operation over existing wires that were originally intended for flip-flop capabilities of the USB-C connector. Starting with the USB 3.2 specification, USB-IF introduced a new naming scheme. To help companies with branding of the different operation modes, USB-IF recommended branding the 5, 10, and 20 gigabits per second capabilities as SuperSpeed USB 5 gigabits per second, SuperSpeed USB 10 gigabits per second, and SuperSpeed USB 20 gigabits per second, respectively. In 2023, they were replaced again, removing SuperSpeed with USB 5 gigabits per second, USB 10 gigabits per second, and USB 20 gigabits per second, with new packaging and port logos. The USB 4 specification was released on the 29th of August 2019 by the USB Implementers Forum. The USB 4 2.0 specification was released on the 1st of September 2022 by the USB Implementers Forum. USB 4 is based on the Thunderbolt 3 protocol. It supports 40 gigabits per second throughput, is compatible with Thunderbolt 3, and backward compatible with USB 3.2 and USB 2.0. The architecture defines a method to share a single high-speed link with multiple end device types dynamically that best serves the transfer of data by type and application. During CES 2020, USB-IF and Intel stated their intention to allow USB 4 products that support all the optional functionality as Thunderbolt 4 products. Because of the previous confusing naming schemes, USB-IF decided to change it once again. As of the 2nd of September 2022, marketing names follow the syntax USB XGBPS, where X is the speed of transfer in gigabits per second. The operation modes USB 3.2 Gen 2 by 2 and USB 4 Gen 2 by 2, or USB 3.2 Gen 2 by 1 and USB 4 Gen 2 by 1, are not interchangeable or compatible. All participating controllers must operate with the same mode. A USB system consists of a host with one or more downstream facing ports, DFP, and multiple peripherals, forming a tiered star topology. Additional USB hubs may be included, allowing up to 5 tiers. A USB host may have multiple controllers, each with one or more ports. Up to 127 devices may be connected to a single host controller. USB devices are linked in series through hubs. The hub built into the host controller is called the root hub. A USB device may consist of several logical subdevices that are referred to as Device functions. A composite device may provide several functions, for example, a webcam video device function with a built-in microphone audio device function. An alternative to this is a compound device, in which the host assigns each logical device a distinct address, and all logical devices connect to a built-in hub that connects to the physical USB cable. USB device communication is based on pipes, logical channels. A pipe is a connection from the host controller to a logical entity within a device, called an endpoint. Because pipes correspond to endpoints, the terms are sometimes used interchangeably. Each USB device can have up to 32 endpoints, 16 in and 16 out, though it is rare to have so many. Endpoints are defined and numbered by the device during initialization, the period after physical connection called enumeration, and so are relatively permanent, whereas pipes may be opened and closed.